morning, good afternoon, and good evening, depending on where in the world you're joining us from. Welcome to our webinar, Leveraging Data Beyond Text, Multimodal AI at Scale, brought to you by our friends at Vespa.ai. I'm Brian Mink, co-founder and president of Data Science Connect, the world's largest data and AI community. Today, we're excited to welcome hundreds of attendees from all over the world to discuss how to unlock the potential of multimodal AI at scale. We'll explore how to architect systems that can retrieve, rank, and serve content across text, images, and video, all while maintaining low latency, high relevance performance. Using Vespa.ai as our foundation, we'll get into the practical mechanics of multimodal retrieval, blending embeddings, applying dynamic filtering, and optimizing ranking strategies. The goal? Delivering scalable, real-time AI experiences that go beyond text and support use cases like recommendation, moderation, and knowledge extraction. We're honored to hear from two distinguished experts today, Zohar Nissare-Houssen, Strategic Lead at Vespa.ai, and Bonnie Chase, Director of Product Marketing at Vespa.ai. Before we begin, a few housekeeping items. To make this feel a little more in person, we suggest you add a photo to your profile and include your bio, LinkedIn profile, and any other information you want your fellow attendees to see. Next, please take advantage of the Q&A and chat features in the right sidebar. The speakers will be addressing your questions throughout the webinar, so be sure to upvote the ones that you'd like the speakers to address. And finally, to learn more about how to leverage multimodal models in your AI journey, check out the call to action below throughout our webinar from our sponsor, Vespa.ai. Now, without further ado, I'd like to welcome.
Thanks so much. Excited to be here. Thanks everyone for joining. To give you a quick overview of what we'll talk about today, I'll share a quick overview of Vespa. We'll talk through some use cases for scale, accuracy, and multimodality, and then share more about Vespa's backend and how we're actually able to support multimodal AI at scale. Then Zohar will walk you through video retrieval specifically, and then share a demo. Now, when we think about multimodal data, there are concepts that apply across modalities. This includes text, images, and videos. So talking about scalability, you want to be able to index billions of documents, images, videos. Those larger items generally require more scale. You want to be able to get accuracy. We know about getting accuracy from text, but this also applies to videos and images. And finally, you need to be able to capture context. And this is where, when it comes to multimodal RAG, this is where systems generally struggle with, because vectors alone are not enough. So let me go ahead and walk you through who we are, what we do, and some of those use cases. So for those of you who aren't familiar with Vespa, we are a platform for building and running real-time AI applications. So this can include anything from RAG and agentic AI to recommendations and hyper-personalization. Now, when you look at the search landscape, you generally have two categories. One are the vendors that really started with text origins. So these are those platforms like Elasticsearch and Solr. Then you have these up-and-coming vector databases. So they started with vector origins. Now, over the last year or two, both circles have kind of started adding on hybrid search or vector search, depending on where they had gaps. But when we look at Vespa really originated with hybrid vector search, starting with vectors back in 2014. So when Gen AI became popular and more accessible, Vespa was already set up to handle the large-scale multimodal demands that enterprises want to put into production today. So I'll walk you through a few of those customer use cases to give you an example of how we were able to help these companies. The first one is Spotify. So I'm sure most of you know Spotify. They are the leading music streaming platform. Worldwide, they have over 640 million monthly active users with a content library of over 100 million songs and over 5 million podcasts. So as you can imagine, large scale. Now with Vespa, Spotify enhances its ability to deliver precise and personalized content recommendations in order to improve the user experience on its platform. So as an example, I'll walk you through one of the examples, which is podcasts. Now, Vespa indexes not just massive amounts of data, but when we think about those over 5 million podcasts, it's every single word in every single podcast. So in this example, let's say you don't remember what a podcast was called, but you do remember some of the things that it talked about. So you can do a search with some of those, some of the things, phrases, things that were said in the podcast, and Vespa will retrieve the most relevant podcast. So here we're embedding the documents in a query space. We're using vector similarity. We're doing the re-ranking to improve accuracy, and then returning the most relevant content that matches the user's meaning. So again, this is an example of large scale search with Spotify. Perplexity is another example of the scalability needs. Now, Perplexity leverages the Vespa platform to provide that robust foundation for their RAG AI application at web scale. And again, this is to ensure scalability and real-time performance for high query volumes. They have over 1.5 billion document index, and they're targeting over 10 billion by the end of the year. So again, large scale data, a need for real-time response, and high accuracy. So Vespa on the back end is doing the retrieval. So anytime someone asks a question in Perplexity, Vespa is in the background retrieving the most relevant and up-to-date information, ranking it to get the most accurate details, and then returning that accurate information to the LLM to generate that answer. And through customization capabilities, Perplexity can really tailor that to their needs and what their business needs are to ensure that they're able to get the most accurate response for their users. Now, Safe Kiddo is an application that uses Vespa across multiple use cases. So Safe Kiddo is a modern safety assistant, which was developed by Info2M and powered by Vespa technology. And this application, I'm a big fan of this because it's designed with a clear goal, which is to detect and respond to online threats in real time, which protects children from harmful digital content the moment it appears. So some of their core features include instant detection, which identifies offensive messages, bullying, and harmful content within milliseconds. They have smart response. So this provides contextual guidance on what actions to take next. So whether that's, reporting it to the police or flagging it, or whatever those actions may be that they've kind of set up for those responses to be. They do location intelligence. So this actually attaches geographical data to physical world content, which enables rapid intervention. So let's say you see, there's a very offensive symbol graffitied on a wall, the authorities are able to identify where that is and then take action then. And then multimodal protection. So here, monitoring text, images, screenshots, memes, using advanced vision language models. So Vespa serves as the AI backbone behind Safe Kiddo, which enables real-time vector and hybrid search, processing both structured and unstructured data. We do the advanced tensor operations, which I'll talk more about later, for understanding the nuanced expressions of hate. Multilingual and contextual retrieval for global application, late interaction ranking to prioritize the most critical threats first, enterprise-grade scalability to handle the millions of users simultaneously, and then, of course, fast model updates and CI/CD integration for rapid iteration so they can continue to improve and enhance their application. This one, I love this app. It's very, important. And then Vinted. So Vinted uses Vespa for recommendations and personalization. Now, Vinted is an online platform for buying and selling secondhand items. This platform enables users to list, discover, and purchase pre-owned items. And with Vespa on the back end, we offer a few different things. So one is the advanced search functionality that allows users to find items that fit specific needs and preferences. And this is from, they have over 1 billion searchable items for sale. So again, we're talking scale as well. Our recommendation engine suggests items based on individual browsing and purchasing habits, which really does increase the likelihood of conversions. And these recommendations aren't just based on, most people do this. It is based on what that specific user has interacted with, they've done thumbs up because they like this type of item. So it really is personalized to each user's journey. So that personalization shapes each user's journey according to their style and shopping behaviors. And then we offer those tailored suggestions. So whether it's trending brands or favored categories. So as we, look at these examples of different customers, there's the multimodal capabilities, there's large scale, there's real time availability. So I want to talk through a little bit about how we're actually able to do that. Now, obviously, processing massive amounts of data with low latency isn't easy, and it takes more than just fast hardware. It requires a fundamentally different systems architecture. So most traditional systems follow the same pattern where data is stored in one place and processing happens somewhere else. So this is typically a compute cluster. Now that setup might work for small scale workloads, but it does break down at scale. And this is because moving large amounts of data over the network is too slow, and the gap between processing speed and network bandwidth keeps getting wider. So Vespa takes a different approach. We really invert that architecture and we bring the computation to the data. So with Vespa, data, indices, and machine learned models are all co-located on the same physical nodes. So that means ranking, filtering, or embedding comparisons can happen locally without those expensive network transfers. So this inverted architecture really unlocks a few different things. One is the faster performance. So that because there's no waiting on data movement, things can happen rapidly. And that also brings you that lower latency, even at internet scale, as we can see with Perplexity. This also brings better cost efficiency since compute can work directly on local data. It reduces both the infrastructure and operational overhead. So just as an example, if you're ranking a million products for a search query and the data and ML models are on the same node, Vespa can compute relevant scores instantly. Whereas in a traditional setup, you'd have to pull that data across the network first, which is slower, more complex, and more expensive. So that's why colocation is at the heart of Vespa's architecture and one of the key reasons it's able to deliver real-time AI experiences at massive scale. So because of that architecture, Vespa is also able to deliver low latency responses, even while processing massive data sets. So whether you're ranking products, generating recommendations, or powering an AI assistant, we can execute complex queries and machine learned models in just milliseconds. And it's not just fast for small queries. Vespa maintains that low latency even when you're handling millions of documents, thousands of queries per second, or real-time signal updates. It really is built to scale without slowing down. And this leads to Vespa's ability to handle real-time data at scale, both for serving and updating. And I know a lot of platforms say real-time, and every write in Vespa is real-time, which means you can update your data and have those changes reflected in queries immediately with no batching or waiting for index rebuilds. Vespa also supports true partial updates, so you can modify just the fields you need, whether it's behavior signals, prices, inventory levels, or ad bids. So there's no need to re-index the whole document. So this really makes Vespa ideal for use cases where freshness matters, like recommendations, ad serving, personalization, and even dynamic prices, even dynamic pricing. And of course, it's fast. So Vespa can handle over 100,000 field updates per second per node, which means it scales effortlessly, even when signals are constantly changing. So it really is built for scale. Now, when we think about accuracy, that really does happen in the retrieval and ranking phase. So, when we look at Vespa's retrieval phase, it really does support a wide range of capabilities. So this handles the structured and unstructured data side by side. So you're able to search across text, filters, metadata, and even embeddings all in one query. You can use Boolean logic, filtering, and advanced operators like WAND or efficient top case search. And for vector search, Vespa supports both KNN and approximate nearest neighbor retrieval, and even multi-vector matching like token level or patch level embeddings for text and image. So moving to ranking, Vespa uses a distributed multi-stage ranking architecture. So distributed ranking means the actual scoring happens on the same nodes where the data resides. So again, this is avoiding those expensive network transfers. The phased ranking lets you allocate compute more efficiently. So you're able to apply the lightweight scoring early and save the heavy ML models for the most promising candidates. And at each stage, you can apply custom business logic or machine learned models depending on your use case, from personalization to ad bidding to content ranking. So really tailoring the ranking to how on your business needs. Vespa also supports dynamic multi-purpose ranking, so incorporating real-time signals like user behavior or price changes, and works seamlessly with metadata like user profiles, product attributes, or content quality scores. And you can also define multiple rank profiles over the same data, which is perfect for A/B testing, personalization, or different use cases like search and recommendations. So you can really see how, through the advanced retrieval, ranking, and inference, companies like Perplexity and SaveKiddo and Spotify and Vinted are really able to tailor the ranking and the accuracy to their needs. Now, this last piece that I want to talk about before we move into video retrieval is the advanced tensor support. And I think this is the piece that when you're looking at working with multimodal data, this is the piece that's more important. Vespa uses a powerful, flexible tensor framework to represent and process data that is especially useful for multimodal data. These are really the next stage beyond vectors. So we know vectors as a flat one-dimensional array of numbers. A tensor, on the other hand, is a multi-dimensional array of numbers. So it's taking it from one to multi-dimensions. So that enables it to support multi-dimensional data like videos and images. Now, you can encode different modalities into vectors, but there are downfalls in doing that. And the first one is you lose structure. So if you're just working with the one-dimensional data, you lose structure. So an image vector, for example, will lose spatial relationships. So where the objects are in the image. A text vector loses token level detail, which word had what embedding. And a video vector collapses time. So there's no way to separate frames. You also can't combine modalities cleanly with just vectors. If you want to search across text, images, and video and compare them meaningfully, you really need a way to represent and align different modalities. Tensors allow you to store token or patch level embeddings. You can have per modality dimensions like token, embedding, frame, region, channel, as an example. And you can include metadata like timestamps, bounding boxes, or modality types. And vectors can't express those relationships because they're flat. And when you want to use techniques like Colbert, which are late interaction of text token embeddings, or ColPoly, which is the multimodal patch retrieval using polygemma, those advanced retrieval methods need more than vectors. They need multi-dimensional tensors to be able to store multiple embeddings per document and interact with queries in a fine-grained way. So without a tensor framework, you'd have to hack this together manually, which again, doesn't scale. So tensors really do provide that better multimodal representation, interaction, and scalability. And they give you the flexibility and structure, the compatibility with multiple data types, and the fine-grained retrieval across modalities. Now, I know I shared a lot of information, especially about these tensors and how they work. And so I'm going to hand it over to Zohar now to walk through video retrieval at scale so we can kind of see how this works in action.
Thank you, Bonnie. Okay, so based on everything that Bonnie explained, a very good use case to demonstrate multimodal retrieval, for AI application is video retrieval. one of the reason as well is that for being a very good illustrative use case, we are seeing more and more enterprise use cases for video retrieval that are emerging, right? Like everybody wants to do more with the unstructured data. There is a lot of work being done with documents. Bonnie shared some of the examples you can implement with Vespa for document understanding using embedding models like Colpali. But for video, we are seeing some use case here just at the Data Science Connect conference this spring in New York. We had a few interactions with clients which were looking for video retrieval use case, and those were, for example, hyper personalization and content serving for media marketplace, right? So it is a global media company, and they have a ton of content that they wanna resell to across the world to other TV station or streaming service or whatever. So they want to do just beyond keywords and metadata. They want the customers being able to do more fine-grained retrieval into what is in the actual contents of the video, right? Another use case that was brought to us was video analytics for media advertisement company, right? So if a end client from an advertiser company want to measure the effectiveness of a campaign, maybe they wanna see how many times the logo of the company was in display during a game that was broadcasted live during Super Bowl, for example, right? Like at which exact section during which moment was the logo in display, how many times, for how long, right? So these are very much very sophisticated use cases for doing video retrieval, right? So how do you address this with a platform like Vespa, which is really suited for this use case? There's still a design phase for this. You need to make sure to ensure, first of all, high quality retrieval, and secondly, for anything you do at Vespa, we want to be able to ensure to have this design work at scale, right? Next slide. So, how do you really implement this, right? So what you want effectively to achieve is to leverage, some of the state-of-the-art video language models that are on the market, right? Some of them are also open source. Here we did leverage models from 12 Labs in the context of this demo asset. And in order to implement a contextualized video retrieval at scale, we leverage two sorts of video understanding model, right? The one model from 12 Labs essentially allows you to interact with your video, to summarize the content of the video, generate some content, like it could be keywords, it could be any kind of metadata creation, it could be obtaining a summary of what's happening in the video. And the second thing that we need is essentially a powerful state-of-the-art multi-modal embedding model. And 12 Labs provide you that and provides you an embedding model that allows you any search-to-search modalities across video. What do we mean by any-to-any search? That means that you could literally, submit a frame of the video that you're looking for, and it would be able to retrieve in which section or chunk of the video disappears. Or it could be a text description of a scene that you're looking for in a particular video. So you should be able to retrieve it. It could be an audio portion of a video, and you want to be able to retrieve where exactly in the video this audio section was. So their embedding model is able to do that. So we can leverage that to actually generate those embeddings and store them in Vespa, right? And Vespa is really the best class platform for this use case, like Bonnie explained to you previously. Our flexible tensor framework is able to, out of the box, able to store the multi-vector embeddings that these models generate using our flexible tensor framework. We are able to preserve high quality accuracy using our advanced multi-phase ranking. We are able as well to do a hybrid query, which kind of does a query across lexical search on the metadata of the video and the actual content of the video, right? Plus, Vespa is as well a platform scalable. So if you want to scale this use case to millions or hundreds of millions of video, it will still work with Vespa. We are just a distributed and scalable platform. Next slide. So in Vespa, let's a little bit deep dive into the design of video retrieval in Vespa, right? So one of the things you can do in Vespa is any piece of data is represented as a document. And for Vespa, any piece of data can be a combination of attributes, so structured attributes, yeah, like you would find in a relational SQL table, like, maybe a date of the video, maybe, metadata attributes, tag like the camera feed from which the video is coming from, the genre of the video, like the category. So here, what and then you can also store multimodal data embedding using our flexible tensor framework, right? So what we did in this case is we choose a sample of videos and we used some of the video understanding model to generate the actual metadata about the video. So the title, we had the title of the video as a metadata, but the video summary, like what happens in the video and the keywords are actually generated using a video understanding model. So we want to have that as metadata and make it a searchable lexical field attribute. And then the actual embeddings of the video themselves. So when you look at what this video understanding embedding model provides you, it's going to chunk your video into sections. By default, this has 6 seconds with this model. And for each chunk of the video, it's going to generate a very rich, contextually and semantically rich embedding, which is going to encapsulate everything that happens in that frame, like from the scene description to the audio to any text that in within that video, that's going to be captured into these embeddings of dimension 1024. So what we are doing in Vespa is that each video is represented as a document, which is a set of associated metadata, and the actual tensor, which is a multi-vector embeddings of every single chunk of 6 seconds of this video. What this design that you can achieve with Vespa allows you to do, it will allow you to do contextualized retrieval, which I just mentioned earlier, right? What does this mean, right? So let's say you're looking for a sunset in the Grand Canyon, but that's a scene from a Western flick, for example, right? So if you do just a purely an embedding search, it's going to give you, hundreds of sunset scenes, in the Grand Canyon. That could be from, content from the Discovery Channel, National Geography, or any, documentary on U.S. National Park. But what you're actually looking for is, no, the context of this is that I'm actually using for a Western movie of a certain year with John Wayne, maybe, I don't know, and which shows me a Grand Canyon sunset, right? So this is what you're doing. You are actually, this document design will allow you to do this hybrid multimodal search, which is rich contextually and contains a mix of structured attributes, like maybe the year. We are not doing it in this example. Could be the year of the video. It could be the actors that are playing. It could be, keyword search based on the abstract of the video, on the genre of the video, and the actual description of the scene itself. So one of the things that Vespa allows you to do, right? So what we are doing here is, Bonnie just explained to you the ranking strategy that you can implement with Vespa, right? So many of these, semantic search system out there will not allow you a lot of flexibility in terms of how you rank the relevancy of your documents, because this is not an exact, deterministic search, right? You are just looking based on what is the top K content that is matching what I'm looking for based on your user intent. So with Vespa, what you can do is you can implement a multi-phase ranking strategy. So in this case, what we are doing is, so by advanced ranking, we mean that you essentially define yourself using, a mathematical formula and using some primitive out of the box like BM25, which is like a normalized term frequency, document frequency type of metric common in lexical search. It could be any custom function of your own. So you define your own ranking expression, right? So in this case, what we are doing something fairly simple but powerful, which is, okay, I want to first rank based on a lexical search on the concatenation of the metadata, so the title of the video, the keywords, and the summary of the video that I generated with the video abstract. And after getting my top K candidates out of this, I'm going to do a second phase ranking, which is actually where I'm going to compare the video embeddings chunk by chunk with what I'm looking for to do a more granular ranking. So ranking is computationally expensive. Using this method allows you to preserve the high quality accuracy and retrieval while not sacrificing performance. So the actual, what is by hybrid query, right? What do we mean by a hybrid query in Vespa across this set of corpus? So in this example, what we are doing, the user query is, I'm looking for a video sample showing Santa Claus on his sleigh, right? And I'm embedding as well the actual query term using the same video understanding, video embedding model. And what I'm doing here is a hybrid query where I'm saying I want to scan my corpus of video where I want to do a lexical search across the title, the content, and the keywords that are associated to a video. Sorry. And along with that, I also want to do a semantic search of the description of the scene that I'm looking for across every single segment that of 6 seconds that I have across this video. So Vespa allows you to do this type of multimodal hybrid query. I could have added maybe some structured attributes that the video had to be for a certain year, or the list of actors in the video should have this Hollywood star and which not, right? If you're looking at surveillance video, for example, it could be a given camera feed. It could be a range of timestamp of the video looking for. It could be a given location that you are monitoring. So, you can get extremely granular in defining the context of where you are, what type of video you are looking for. And then granularly within that entire video feed, you can get to the chunk which contains what you are exactly looking for, right? So this query, for example, we will do a best lexical match based on the user query terms versus, my metadata field. And it will do a proximity search for the top 10 segments. So the top, 6-second segments of the video versus my query terms, right? So I want to show you a quick demo. All of this information and this demo is public. We are going to share with you the links here. You will need, in order to run the same use case, you can spin up a Vespa.ai trial account. You can get a 12 Labs API key, right, as well. They will give you, like, I think 1,000 minutes worth of credits. That's more than enough to run this sample. And in this use case, essentially, we used some 3 cartoons from the Internet Archive, which is a public website. And we have a very detailed notebook and blog, which takes you through step by step on how to build this use case. It's an excellent use case that shows you how to enable, a multimodal retrieval using Vespa. So at this point, let me share my screen so I can kind of walk you through really quickly this demo. So in this case, I have here a Jupyter notebook that kind of walks through the entire data engineering. This notebook is actually public. It's on the Vespa blog. Vespa blog and Vespa GitHub. Vespa, by the way, is fully open source. And then I can quickly walk you through all the data engineering step to build this multimodal retrieval, right? So I'm not going to run the whole notebook in the interest of time, but I want to show you, the key steps, right? So here, in terms of library installation, you just need our Python API. So Vespa has a Python API, which comes in very handy to implement your, AI integration. You need to install the Vespa CLI and the 12 Labs API, right? That's pretty much it. You need to import certain package. You need to get a 12 Labs API key. You can sign up here on the link. You do need a tenant name you need to spin up a trial account, get a tenant name for Vespa, and give a name for your application. And I'll just show you the interesting part, right? So the first thing that needs to happen is the URL of the video, like I explained to you, these are all for Internet Archive. And there's a sample of 3 videos. You may be familiar with the end from Blue Sky Studio. It's the squirrel scene with the acorn in the Ice Age cartoon, right? Where at the end he just put the acorn on the ground and it just creates chaos. This is Twas the Night Before Christmas, which is like a classical cartoon about Santa Claus, a 20-minute cartoon, right? And then some random Warm in the Apple animation video, right? So we are just doing this over 3 videos. And there's a few steps in here to upload the videos, but this is the metadata generation step, right? So for each video, we are leveraging the video understanding model in order to generate the summary of the video. So we just pass in the URL and we prompt that, hey, I want to generate an abstract of the video serving as a metadata up to 5 sentences. So by default, it will generate you an entire very detailed description of the video. So for the summary, we just want something like 5 sentences and some keywords, about the video, right? So we do this for the 3 videos that we have that we're going to store as part of the metadata. And then we are generating the embeddings of the video, right? So for each video, we are creating an embedding task. And you can see that for each 6-second segment, it's going to generate, an embedding. And you can see what this looks like, right? So for the first video, you can see for each offsets of 6 seconds, it's actually going to generate for us, 12 segments. And for each segment, we're going to get an embedding that is of float type, float 32 type, and 1024 in dimension. Here, just for readability, we just truncate to the first 5 items, right? So it's kind of straightforward, right? Each video, we get the offset of 6 seconds by default. That's actually customizable. You can choose smaller and longer offsets. And for each offset, you get an embedding. And then you can actually deploy the application in Vespa. So that requires a document schema, which is what I showed you earlier in the presentation, the title, the keywords, the video summary. This is my ranking function, right? Like I want to be able to get a lexical score based on the lexical search on the title, keyword, and summary. And in a second phase ranking, I want to do a semantic search of my query embedding that I'm going to embed using the same video understanding model, doing a similarity search across every single chunks of the video. And then the application is ready to deploy. I can feed that to Vespa, right? So in Vespa, any document needs to have an ID and the different fields, which are, the one I explained, the URL of the video, the title, the keywords that we generated, the video summary, and then my embeddings, right? I created 3 documents. And here you can see a sample of the data. Here, the first video is that squirrel video from the end. And it has the summary, it has the keywords, the title, and embeddings for every single 6 second, chunk of the video. It's essentially an 18-second video here for that given clip. And for each chunk, I have my embeddings. I'm only displaying the first 3 for readability purpose. So you kind of get an idea on how we store multimodal data in Vespa, right? So it's a combination of structured text and the actual embeddings using our tensor framework. So you can see here, this represents the tensor, right? Which is essentially a multi-vector structure. And each vector represents a chunk, the embedding of the chunk of the video. And Vespa is able to accommodate this natively in order to store index and be able to do any kind of retrieval operation using any tensor operation. So in this case, the tensor operation is simply a dot product and a cosine similarity search between the query term and the embeddings. So one that is all done, I'm ready to do a query, right? So here you can see these are the two steps of the notebook that I will actually run. So here I'm looking for Santa Claus on his sleigh, right? So I want Vespa to essentially retrieve me from my sample of 3 video, and every single 6-second chunks that I've stored, I want to find out if any video shows a Santa Claus on his sleigh, right? I had actually developed this demo during Christmas, so that's why I chose this. So the first step is essentially to using the 12 Labs API is to generate a text embedding corresponding to my query term. So I have it here. This is, I'm going to generate a 1024 embedding size representing my query term. And then I'm ready to submit my query. So this query is actually running live. You can see it takes literally milliseconds. And this is where I'm doing my query, right? So I'm doing from the corpus of my video, I want to do a lexical search across all the metadata with the keyword Santa Claus on his sleigh. And I also want to do a semantic search across, every single chunks embeddings that I got as part of my multimodal, multi-vector embeddings, and the embeddings of my query term. So the result of this, it's retrieving us as a document ID that video called "Twas the Night Before Christmas," all the metadata associated of the video. The semantic search is actually done against the title, the keywords, and the video summary. And then it's able further to tell me that, by the way, the most relevant chunk that matches what you're looking for is in cell 212. So out of the, all the chunks of video that I have, it is the chunk number 212, which is the most relevant, video containing your what you're looking for. And it gives me in seconds the start offset and the end offset. And it tells me this is the cosine similarity score, right? Which is the highest that I got for the query term against what you're looking for. And then I can do quickly run some, data cleansing step to be able to make that result more consumable, right? So when you look at this, what it displays, this pandas data frame is giving me the top 10 chunks that were, there's a Santa Claus on this particular video, right? Like that's the way I did it, right? Give me the top 10 similarity search, and it's giving me, all the offset in the video ranked, sorted by decreasing similarity score, where I might have a hit for what I'm looking for. I'm doing one additional cleansing, like a data transformation step to interpret the result better. And it's able to concatenate all these segments and give me in minutes, seconds, ordered by increasing timestamp, which are the segments of this video which contains information about a Santa Claus. So the top segment is included in this particular section of the video. So let's just take a quick look at it. So 20 minutes, 39 seconds to 21:21, right? So this is the video. And let me just fast forward to 20. Was it 2039?
No, gave the luster of midday to objects below.
Yeah.
And what to my wondering eye should appear but a miniature sleigh and 8 tiny reindeer, with a little old driver so lively and quick, I knew in a moment it must be Saint Nick. More rapid than eagles his coursers they came, and he whistled and shouted and called them by name.
Now Dasher, now Dancer, now Prancer and Vixen, on Comet, on Cupid, on Donner and Blitzen, to the top of the porch, to the top of the wall, now Dasher.
So that's the demo, actually. So you can kind of see, how we are able to retrieve out of all the segments, out of all the videos, using a contextualized search, be able to narrow down the video that we are looking for. Yeah, that's all I had for you today. We can maybe switch to the Q&A if you have any questions.
Yeah, and I think, Zohar, there is one question that is about any suggestion for finding a balance between latency and cost when deploying multimodal, especially when blending vector search.
So I think this can come from there are many techniques, right? Like you can play with the video with the embeddings, with the embeddings precision and dimensionality, for example, to reduce those. Some of the techniques that you can use is Matryoshka reduction. You can use binary quantization as well. So there are many techniques that allows you to scale this, like especially with our multi-phase ranking. What we can recommend to run this at scale would be, for example, in a first phase ranking, you can use the binary quantized or a lower dimension vector if your embedding models support that. And in a second phase, so after doing the coarse retrieval, in a second phase, you can re-rank better with higher precision, higher retrieval on a smaller, set of re-rank, right? So that would be one way to optimize it. There are many ways of doing this, right? Like, but most of those will revolve around, the embedding models that you are using, if they support a reduction in terms of dimension precision, all the way down to binary quantization, and be able to find the right balance between accuracy and latency/cost.
And I just posted a link to one of our blogs that talks about some of those things as well. Looks like that's the only other question we haven't answered yet. So Brian, unless you can see any others, I think we can wrap.
Sounds great. Well, thank you both for joining us today. Really enjoyed the presentation and insights. For those of you in the audience, if you missed any of the webinar today or want to rewatch anything, the recording will be available at this same URL just a few minutes after the webinar concludes if you refresh the page. And we'll also send out a link to the YouTube recording tomorrow as well. So thank you again to Bonnie and Zohar, excellent presentation, and to our partners at Vespa.ai for making this webinar possible. And we'll see all of you again next time. Thank you.
Thank you.
Thank you.